Okay, so here's the problem, and it was from one of the practice problems in your textbook. And the problem had to do with a 2100 kilogram car that was parked in a driveway, and then it starts rolling out of the driveway. The driveway is at a grade of 20 degrees, so we have the car starting at 0 meters per second because it's at rest, and then it starts backing out of the driveway, and friction force is working against it. They said the force of friction was 4,000 newtons. At the end of the driveway, when the car reaches the end of the driveway, it's got a final velocity of 3.8 meters per second. And what the question was is how long was the driveway? So they want to know the distance of the driveway. We can solve this problem with the work-energy relationship, work-energy theorem. So let's try and do that. The work-energy theorem says that well, you know what? Let's not put it there. The work-energy theorem says that the net work is equal to the change in the kinetic energy of the object. The net work done on the object is equal to the change in the kinetic energy of the object. And from last time, we remember the kinetic energy, change in kinetic energy, which is the final kinetic energy, 1/2 mv final squared, minus the initial kinetic energy, which is 1/2 mv initial squared. That'll be the net work. We also know that net work is the net force times the distance or the displacement involved, so long as the net force that we're talking about is running parallel with the displacement. Otherwise, there's going to be a cosine of an angle that you're going to have to put in here, cosine of the angle between the net force and the displacement. But in this case, the displacement, which is the length of the driveway, d, is the length going down this ramp. That's what we're trying to find. What is that? So let's look at the forces involved here. We have, of course, the weight of an object, which is straight down, and then we have, of course, the force normal, and then we're going to have friction, which is going to be in that direction. So let's put a little arrowheads on here. Here's weight, friction, and our normal force. There's force, friction, and here is weight. Now weight, again, is mass times g, mg. Weight is always mg. And let's now put our axis in here. That is going to be our axis that's going to run perpendicular to the plane, and in this case we want it running, well, undo, let's try it again. All right, good to go. So let's do this. Let's put our components in here. For weight is going to be 1 in that direction and the component in this direction. Remember that this 20 degrees here goes right inside there, so that this component going down the green axis is going to be our weight times the cos of 20, and this component over here is going to be the weight times the sine of 20, weight sine 20. Remember, sine is always down the ramp, and it's this angle we're talking about. So what was the weight? Its mass was 2100 times 9.8. All right, whatever that value come out to, that's the weight. We take that times the sine of 20 to go the force component of the weight down the ramp. So looking at this then, we find that the net work done is equal to the net force done down the ramp, of course, times the distance or the displacement down the ramp, which is going to be the change in the kinetic energy, and that's going to be 1/2 mv final squared minus 1/2 mv initial squared. So what's the net force here? The net force down the ramp, and again, that's the only one that's going to contribute to work, because now the perpendicular forces, whether it's the normal force or whether it's this component of the weight along this line here, these are perpendicular to the actual displacement, and as we said, they never do any work. Perpendicular forces to the distance it's traveled or the displacement don't do any work. So these don't contribute. The only forces contributing to the work being done down the ramp in this direction, which is the direction of displacement, are going to be from the friction and from this W sine 20. So the net force then is going to be this W sine 20 minus the force of friction, right? So you see that the net force, which is the total or the resultant force, is going to be this guy minus the friction, because it's like a tug of war here. This one's pulling with a certain amount of force, friction's pulling upward. We know that friction was 4,000 newtons because that's what was told. This I calculated to be, well, I guess I didn't write down what I calculated it to be there, but we will do this. This is going to be the equivalent of 2100 times 9.8 times the sine of 20. All right, so this is going to be 2100 times 9.8 times the sine of 20 degrees minus the force of friction, which the textbook told us was 4,000 newtons, and that times the distance that it's going to go down the ramp, because that's the distance it's going to travel, that's the displacement. That's going to be our net work, and this is going to equal 3038.77. This is D. Now we got 1/2 mass. The mass is 2100 kilograms. V final is 3.8 meters per second squared. That's what we said V final was. V initial was 0. It started from rest, so this is going to be minus 0 because V initial is 0. So this term here, 1/2 m V initial, 1/2 m 0 squared, this whole thing's gonna drop out and be 0. So here's our equation. This guy here times D has to equal this here, which I calculated out to be 15,162, I believe. Yeah. And then when we divide both sides by 3,038.77, we'll get D equals to approximately 5 meters. So the distance of this driveway was 5 meters, and we were able to find that distance through understanding the work-energy relationship, this relationship right here, that the net work done on an object is equal to the change in the object's kinetic energy. And the kinetic energy is simple. It's just kinetic energy of any object is 1/2 the mass times the velocity squared. So if you have an initial kinetic energy and a final kinetic energy, it's going to be those numbers are going to be determined by the initial and the final velocities, but it's the change in the kinetic energy that we're concerned with here. So I hope this helped, and that example helped understand the relationships between how to solve problems using work and energy.